This is Mrs. Palmer-Quay with the fourth video for Module 6. In this video, I'm going to be talking about determining empirical and molecular formulas. We are still dealing with stoichiometry in this video, more math, and just remember that stoichiometry lets you calculate moles or masses of a reactant or product from the moles or masses of another substance in your balanced chemical reaction. Also, if you're working with gases, you can go directly from mole ratio to volume ratios. Remember also that we are always working through moles. We use the mole ratio, we use the moles of whatever substance we're considering to go to grams, that we never can go from grams to grams, that we always have to go through the moles. The chemical formulas that you are beginning to become more familiar with may actually represent two different things. A chemical formula can represent the atoms present in one molecule of a compound, and that is more accurately called the molecular formula. Or the chemical formula may represent the simplest whole number ratio of atoms present in the compound, and that is known as the empirical formula. So for an example, our water, H2O, is the molecular formula. In one water molecule, we have 2 atoms of hydrogen and 1 atom of oxygen. And in general, in covalent compounds, the molecular formula is what we have when we use a chemical formula in a reaction. The example on the right, this cube, is an illustration of a crystal of sodium chloride. And you will see in sodium chloride we do not have a distinct molecule that is one sodium and one chloride, but really you have a lattice work, a buildup of one sodium next to one chloride, next to one sodium, next to one chloride, and so forth. And so this sodium chloride formula is actually an empirical formula. It is the smallest whole number ratio of the different atoms in that compound. But when the substance of table salt is made, it is actually a large crystal lattice like this. And many of our ionic compounds, the formulas are really empirical formulas. In addition, the molecular formulas that we have with covalent compounds may or may not be empirical formulas. In cases where your molecular and empirical formula are the same, you have a substance such as water, where you see that we have 2 moles of hydrogen and 1 mole of oxygen in every molecule, or a mole of molecules, and we cannot reduce that formula to any smaller unit. But in the case of glucose, we have a difference between the molecular formula and the empirical formula. The molecular formula is the C6H12O6, but this is not the smallest whole number ratio between the atoms. This formula does not represent the empirical formula. The empirical formula would be CH2O. It's like you're factoring out a 6 in algebra class. And so with the covalent compounds, even though the formulas are molecular formulas, there may be an empirical formula possible for those covalent compounds if you can reduce the subscripts to a smaller whole number. So how do you calculate an empirical formula? Typically, the situation is something like this. You have a substance that is decomposed, and you are given the percent of the constituent atoms by mass. So the one we're going to work with today says a compound is found to have by mass 48.38% carbon, 8.12% hydrogen, and the rest being oxygen. So what is the empirical formula? There's a helpful rhyme that I found. I didn't develop this. It was developed by a teacher named Thompson. But this helpful rhyme outlines the steps to calculate an empirical formula. It says percent to mass, mass to mole, divide by small, multiply till whole. So step 1 says percent to mass. What does that mean? Well, in our problem, we are given values that are percents. 48.38% carbon, 8.12% hydrogen, and some unknown percent of oxygen. If we assume that we have a 100-gram sample, just like 100%, then we can go directly from percents to grams. Instead of 48.38%, we have 48.38 grams. Instead of 8.12%, we have 8.12 grams. And then we can subtract these two known values from 100 to give a value of 43.50 grams of oxygen. You don't have to assume it's a 100-gram sample, but that's going to be more math. If you use 100 grams and 100%, it works out really nicely. Also notice that the hydrogen and the oxygen are not in a diatomic state. We are not talking about hydrogen and oxygen gas as an element. We are talking about hydrogen and oxygen in a compound. So make sure you don't mistakenly count these as a diatomic element, but you are only using individual atoms for hydrogen and oxygen or any of the other ones that exist as diatomics when they're in the elemental state. After doing percent to mass, the next step is to take the mass to mole. And this process should be something that you're very familiar with by now. It is just the calculation of going back to the periodic table and looking at the amount of grams present in 1 mole, multiplying by that conversion factor. So for carbon, in 1 mole, we have 12.0 grams. In hydrogen, in 1 mole, we have 1.01 grams. And in oxygen, in 1 mole, we have 16.0 grams. If you go ahead and do the math with these three values, you will see that we have 4.03 moles of carbon present in this gram value. We have 8.04 moles of hydrogen, and we have 2.72 moles of oxygen. Now that you have the moles, the next step is to divide by small. That means you take the different mole values and look to see what is the smallest. Of course, between these three, the smallest will be the 2.72. And so you're going to divide each of these mole values by 2.72 moles. And that's going to cancel out your mole value, and we're just going to be left with a number, which is what you want because we're eventually going to be heading towards the subscript in our formula. So if we go ahead and divide each of these by 2.72 moles, that allows us to cancel out the mole. If we do the math, we're going to get the values 1.48 for carbon, 2.96 for hydrogen, and 1, of course, for oxygen. The final step is to multiply till whole. And in this case, we're going for whole numbers instead of these decimal places. So first of all, you want to see, can we make any of these whole numbers without doing massive amounts of rounding up? We've got a whole number here for oxygen 1, hydrogen 2.96. Well, that's really not that far away from 3, so it's okay to round that one up to a whole number. But with carbon, we have 1.48, and it would be an awfully big jump to round up to 2 or down to 1. It would be much better to just take that up to 1.5. And then we think about, is there something that we can multiply these three values by that will give us a whole number? What's the smallest number we can multiply these by to end up with a whole number? And of course that would be 2, because if you multiply the 1.5 by 2, we get a value of 3 for carbon. If we multiply the 3 by 2, we're dealing with whole numbers all along here, but we'll end up with 6. And then, of course, the 1 by 2 will give us 2. And these are the values then that are for the subscripts in our empirical formula. They are the smallest possible whole numbers given the data that we have calculated with the mass percents that were given in the equation to begin with. So the final formula would be C3H6O2. And this is the empirical formula for this compound based on the data of the experiment. Now sometimes we're asked to go a step further, and we're asked to compare the empirical formula to a known molecular mass, so that we have been given an empirical formula and we are given a molecular mass to determine the molecular formula. These problems would look like this. A compound is known to have an empirical formula of CH2 and a molar mass of 70.11 grams per mole. So can you use those two values to figure out the molecular formula? In this case, you want to go to the periodic table and see what is the mass of the empirical formula, so that we would have 12 for carbon plus 0.01 for hydrogen. So we'd add that all together and you're going to get 14.02. This is grams per mole. And we would use that with our 70.11 grams per mole to calculate how much larger, we're trying to find a factor of increase, the ratio between the 14, that would be just one molecule of the empirical formula, and the molecular formula, which represents really how many carbon and how many hydrogen are present. So if we take 70.11 and divide it by 14.02, we get a number of 5. So that says that the molecular mass is 5 times greater than this empirical formula mass, so that the molecular formula must be also 5 times greater. And so we'll take this 5 and sort of factor it in to all of the atoms in our empirical formula. So instead of carbon just having 1, it's going to have 5, and instead of hydrogen having 2, it's going to have 10. So this represents your molecular formula, which was calculated based on the empirical formula and a molar mass or molecular mass that is given to you. So these are the two kinds of problems that you need to do when you're considering empirical formulas and molecular formulas. They're just building on the math of stoichiometry that you have been working on, hopefully, and I hope that this video helps this particular process make a little more sense to you.